Okay, guys, so let's do this problem regarding fluid mechanics and has to do with energy losses, okay? So this is the setup. It's already here, and this is the setup. It's not very complicated, but you have a lot of data that you need to take into account, okay? So it seems that there is a deposit here at the left, okay? And then it's flowing water down into another deposit at the bottom, okay? That's basically the idea. Here we have the flow rate. So the flow rate is 0.7 liters per second. Then we have the roughness. This is the absolute roughness of the material of the pipe. Okay, this is the diameter of the pipe. This is the length of the pipe. This is these two are the properties of the fluid. In this case, this is water. Okay, so we have pretty close to 1,000 kilograms per cubic meter, which is water. And then we have this dynamic viscosity also for the water, but I think it's a little bit high temperature. That's why you have this instead of the typical value that I think of whenever I'm talking with about water. It's one times to the minus 3, 10 to the minus 3 pascals per second, but in this case a little bit less because maybe it's a little bit heated up. And then you have these loss coefficients for the accessories. So there is 4 elbows in this trajectory from here to down here. You have two things to consider. One of them are elbows. Okay, there are four elbows, and there's a valve. So somewhere in this trajectory, you have a valve. Okay, this is actually a very harsh simplification of what's going on in a real hydraulic system, because you're going to have at least two valves, the one from here and then at the bottom, and maybe you're going to have a bypass, and maybe you're going to have a check valve, and maybe you're going to have, I don't know, several things. But in this case, it's just straightforward. I would say that almost straightforward. But these things, you have 4 elbows, okay, to consider. They are already giving us these loss coefficients, and we're going to use those values here. What they are asking us to get here is the height from one deposit to the other. How much distance there is from one deposit reservoir from the other. And it's a trick question that I want to discuss a little bit because, okay, so which part of this reservoir regarding which other part of the other reservoir, which one is the height? Maybe this one here, or not? Is that's not the one, or which one is it? So that's something that you need to I'm gonna do it straightforward, but the discussion is a little bit more profound that I'm gonna do. So basically, this is the height that they're asking me to get. And you're gonna say, why not the bottom, why the surface of the water? Why is that? Okay, and that's a very good question. Okay, but the answer is that because at the surfaces of water I know a lot of stuff. So imagine that I'm gonna call this 0.1 and this one is 0.2. Okay, this still reflects the height from one deposit to the other. They are not telling me which part of the reservoir, which other part of the tank or the reservoir, whatever you want to call it. Okay, so I'm gonna pick the surfaces of the water. These are called free surfaces in this language of fluid mechanics, and these free surfaces from 1 to 2, it's gonna be the h, or the height, that I'm looking for in this problem. Why this h and not another possible height from some other position of the tanks? Well, because here I know several things. This is the symbol for free surface, and I know several things. You will know which things I'm going to refer when I'm talking about I know several things. So the first thing that I'm going to do here is to use the general equation of energy, which is this P1 divided by rho G, V1 squared divided by rho G plus HV plus Z1 equals to P2 divided by rho G plus V2 squared 2G plus Z2, and then let's just put HL and HM. So you should be familiarized a little bit with all these symbols, but this is the energy due to pressure. This is the kinetic energy. This is the head of the pump. This is called the head of the pump. In this case, you don't have a pump. I mean, it doesn't say that you have a pump. You could have a pump somewhere here. Imagine that they put a pump here. But since you are letting water flow from upstairs to downstairs, so maybe there's not a big necessity for a pump. If it were backwards, so from 2 to 1, you need something in order to push the water from the bottom to the top of this from 2 to 1. Okay. So in this case, you don't need it, but I'm just going to put it here, the whole equation. C1 is just the potential energy at 1. This is, again, the energy from the pressure at 2. Kinetic pressure, no, kinetic energy at 2, potential energy at 2. And these ones are really important, are the ones that I care about. These are the losses. So these ones are called the main losses, and these ones are called the secondary losses or the accessory losses. But these ones are energy fractions that you want, they are completely unuseful. You don't want these guys to happen. If these guys happen, there is something there that, well, that you don't want to see in this type of systems, but you're going to have them. Okay. So HL has to do with friction losses due to the material of the pipe. Okay. And HM are accessory losses, or secondary losses that has to do with things. Yeah, elbows, it's a thing that obstruct the water. Elbows, the valve also obstructs the water. Exit, outlets, inlets, all that type of things that will modify the trajectory of particles of water or some other fluid there. It will happen. It will produce these accessory losses. These friction losses are because of the friction with the walls. Okay, that's kind of the idea. Okay, so that's the explanation of each one of these terms in this equation. This is a general equation of energy for these hydraulic systems. Okay, so what I'm gonna do, I'm gonna simplify so much this that you're gonna say, well, this is like cheating. Well, it's not cheating. It's already know what you can account for and which things you shouldn't account for. So since I'm putting my 0.1 and 0.2 right where I want to, okay, right where I want to, I can simplify a lot of stuff. So for example, P1, it's not 0, but it's equal to P2. So P1 and P2 are located right at the atmosphere. So the atmosphere is pushing here and the atmosphere is pushing there. So I can think that from 1 to 2, the atmosphere or the atmospheric pressure won't change that much. So I think they are kind of the same thing. Also, V1 is 0 and V2 is 0. These guys are not moving. Maybe, I shouldn't say maybe, but here, the water is moving, so velocity is not 0 there. But at these points, I can pick whichever points I want to. Therefore, I'm going to pick point 1 and point 2. These points 1 and 2, I can consider that the water is not moving. So these are very good points to simplify a lot of stuff. There is no pump. I'm going to think that there is no pump there. And C1 is not 0. I'm going to say, well, this one is going to be C1 and this one is going to be C2, but I'm going to put it later. Okay, so this one going to be the level of the C2. Let's go. Oh, sorry. I was going to say later, but since we already here, P2, we already know what to do. V2, we already know what to do with that V2. Therefore, Z2 equals to 0. I mean, maybe you can say, you can argue, hey, well, you know what, we have this depth of water within the tank, and I'm going to say, well, you know what, I don't care about that depth. I just care about this level here, and this is my reference. I'm gonna call it a 0. I actually don't know if this thing is 0, but for me, this is my floor, this is my bottom, this is my reference, this is my 0. Okay, and therefore the one that I'm looking for is Z1 minus Z2. But since C2 is already equals to 0, therefore the only thing that I'm looking for in this case, it should be the only unknown, is this Z1. I don't know this Z1. Maybe I wanna get it. And now we get to these losses, okay, HL and HM. So long story short, out of all this equation, I got Z1 equals to HL plus HM, which means that the height equals to the losses. So the height that I need to put water into from tank 1 to tank 2, it's equal to the losses. Okay, so the height or this potential energy is compensating for the losses that I'm going to have here from 1 to 2. That's what's going to happen. This is my equation of the energy regarding this hydraulic system. Now, what I'm looking for here is an expression for HL, and this one is called the Darcy-Weisbach equation. Maybe you know it. And HM equals to the equation for accessory losses, V2 squared divided by 2G. Okay, so maybe there's a source of confusion here that I want to explain. We said that V was 0 at 1 and V velocity was 0 at 2. That doesn't mean that everywhere from 1 to 2 velocity should be 0. It's actually not 0. Okay, so there's a place from 1 to 2 where water is flowing. But here at 1, I can say that water is not flowing, and here at 2, water is not flowing. I can consider that, okay? So right at 1, velocity is 0, right at 2, velocity is 0, but in the meantime, from 1 to 2, you know what, maybe V is not 0. That's why these guys are not 0. If these two guys were 0, then therefore C1 equals to 0, and that's like, okay, so this is not real, okay? So I need to find these guys. So what I'm gonna do with those two guys, I'm gonna, put them together. I'm gonna say, well, you know what, FLD plus summing up the case for the accessory equals to V2 divided by 2G. So I'm gonna factorizing V2 divided by 2G. This one is not very I already know that. So I know that G equals to 9.81. Therefore, 2 equals to 2G equals to 19.62. Okay, so this one is a known one. This one is, I don't know. This one is actually going to be a little bit harder. L, I already have it. This is the L, 20 meters. I have the diameter, this one over here. And I have the sum of these guys where I can sum them up. I have 1.1. Therefore, I have 4 of these 1.1s. And I have a valve, just one valve. And I have this guy. So this one is known, right? So if this one is the one that I don't know, I almost have these guys, but still I don't have the velocity. Oh, okay, so I'm gonna get the velocity. So you remember that I have the flow rate. Flow rate equals to 0.7 liters per second. And flow rate, you should know that it equals to velocity times the area of the pipe. This is a pipe, well, maybe this is not the best way to draw it, but this is the pipe going up here. Okay, so I have this and I have the diameter. So the flow rate that it's going through this area, this is the area. So if I see this is the pipe looking from the front, or where I'm looking at the inside of the pipe. Okay, so this one is the area that I'm looking for. Okay, so that one is not very difficult to get. This is the cross-section area, and therefore I'm gonna put in explicit form the velocity. So the velocity is going to be Q divided by A. So you already have Q, and then A is going to be, okay, let's just put numbers. Liters per second, that's the flow rate, divided by pi, okay, because this is a circle, multiplied by the diameter, 1.5 times to the minus 2, 10 to the minus 2, which is meters. I need this thing in meters. Oh, okay, so I'm doing something wrong. I'm going to correct it. Squared and then divided by 4. This is the cross-section area of a diameter of 1.5 centimeters. So I'm putting these centimeters in meters, and I made a mistake. I made a mistake not with the area, but in the flow rate part. So in the flow rate part, I'm going to, this one over here. So yeah, it's correct. This is liters per second, but I need to change it to cubic meters per second because I want this in the international system. So 10 to minus 3 cubic meters per second. That's the same thing as 0.7 liters per second. So I have this one. So if you do the calculation, so V is going to be equal to 3.96. I already have the number here, meters per second. So I have this value of the velocity. So with the flow rate and the diameter, I get to calculate the velocity that it's going through the pipe. Not here at 1, not here at 2, but at the pipe. Inside the pipe, I have that velocity. Okay, I already have this fella here, so I have this guy. The only thing that I'm missing here is this F, okay? So F is the friction coefficient. You already know this thing, maybe the friction coefficient. The friction coefficient. It's dimensionless. Okay, it doesn't have any units, and you can use two things in order to get this friction coefficient. One of them is the Moody's diagram, the famous. Maybe it's famous for you. For me, it's a little bit famous. So the Moody's diagram. Okay. So you have this y-axis F, and then you have the x-axis at the Reynolds number, okay? And here at the right side of the y, you have another y-axis at the right side, and this one equals to the relative roughness. This relative roughness equals to the absolute roughness. In this case, we have 0.15 millimeters divided by the diameter in the same unit. So it's going to be, I don't know, maybe you remember that it was 1.5 centimeters, which is the same thing as 15 millimeters. And that will get you to 0.01. That's the relative roughness of this example, okay? So now you have this value, but you still don't know this Reynolds number. So let's just have, maybe you know that the Reynolds numbers can be calculated as density, velocity, diameter, and then divided by dynamic viscosity. You have everything you need in order to get this Reynolds number. So it's just 992 what was the number? 992.1, okay, multiplied by the velocity, 3.96, and then multiply by the diameter, and it should be in meters. So I'm going to put again 1.5 times to 10 minus 2. This one are meters, and everything's going to be divided by the 0.653 10 to the minus 3 pascals per second. So everything is the international system of units, and therefore my take on this one, so the Reynolds here, what I have here is 90,200. I think it's 200. Hopefully it's 200 because I look like it's like a 7. So 271.22. Remember, these guys, I should say that these numbers are not very relevant. Maybe just the 90,000 is the one that you're looking for. But nonetheless, this is our Reynolds number. And therefore, in order to get this friction coefficient, you need these two. In order to get the friction coefficient, most of the times you're going to need the Reynolds number, and you're going to need this relative roughness. You can use the Moody's diagram, which are these type of lines here. So it's kind of the lines that you're going to see in the Moody's diagram. But since I don't want to use that, I want to use the Colebrook equation. So I want to put here the Colebrook equation. I'm not going to write the Colebrook equation, but you can look for in the internet, or you can Google Colebrook equation, and you can say online. And there are already, calculators for this equation where, again, you need to put the Reynolds number and the relative roughness. These are data that you need to put as input in order to this Colebrook equation. And with that, with these calculators in the internet, you can find that F. In my case, I found that this friction coefficient was around 0.038. It's a very small number, 56 without units. So I already have this friction coefficient, which was the missing part of my whole puzzle. So I think I have everything set or put into place. So I'm going to do it here. Let's just divide this. Therefore, Z1, which I don't know, equals to HL plus HM. In this case, I'm already doing this adding up. So 0.03856, okay, that's F, multiplied by L, so 20 meters, divided by I can put it with point, but let's just put it with the things that I have used. 1.5 times 10 to the minus 2 meters, okay? So, okay, I have this F, and this is LD, multiplied, I need to add up the elbows. So the elbows is 4 times 4 elbows times 1.1, plus, again, because it's adding up, I'm adding up the above, okay? So this is the sums of K's. Okay, and then everything, let me just put this big parenthesis here. Oh, times v squared, which is 3.96 squared divided by 19.62. Okay, so this whole thing will add up. I already had this thing solved. 52.63.6, yeah, 2 points, yeah, sure, buddy. Okay, so 0.63 meters. Okay, so this is the height from one free surface to another free surface of these two deposits, reservoirs, tanks, or whatever you want to call it. And the problem is done. Okay, so we will see each other in another video. Take care, guys.